Hi, got me a quick question.
Go for it.
So, I just wanted to confirm, but last Thursday you said both labs were due on next Thursday instead of this Thursday because
Yeah,
of
yeah,
Thanksgiving.
yes. A week after Thanksgiving.
Oh, December 2nd then.
Yeah, actually, I think isn't it the fourth? I think Thursday's the fourth. Or did you have a Wednesday lab?
That's a Thursday lab.
The Thursday lab. So yeah, I think it's the fourth is Thursday.
No, the fourth is Saturday.
Whoa, man, I'm way the heck off then. Yep, you're right. It was well. Oh yeah, the second. Yeah, gotcha. Yeah,
It's
that's
only like
stupid.
2 days.
I was thinking
Kinda close.
Wednesday was December 3rd, and I knew for a fact it was December 1, but for some reason I added 2 to it. So yeah, you're absolutely right. It's December 2nd. Thanks for catching me on that,
Okay,
Clarence.
okay.
So yeah, and I think I already said it in the dates on the thing. If I didn't, don't worry, it'll be set. You know, the day that you turn it in, because I'll remember it then. But I'm about 99% sure I fixed them all Friday before I went off for the weekend. I say went off, I mean went off grid. Turned my phone off. Got kicked out of Facebook again. I'm in Facebook jail. Hate this. It's my only outlet to political discussion. No one, you don't want to talk politics with your family. My only Facebook, my only political outlet is on Facebook, and this time their AI editor screwed up. I was being complimentary to a lady who had apologized for being ugly to me. I said, "Well, your ugly wasn't nearly as bad as mine as what I did," and they interpreted YOURUGLY as YOUREUGLY, and now I'm suspended for 7 days. Urgh. So mad, and there's it's impossible to contact Facebook. You can send them 1,000 things, and you're never ever going to hear from them. I'm in withdrawal, so I'm literally like, I need some kind of benzos or something to take off the edge. Not really. I don't do any drugs of any sort, legal or otherwise. I take the medication the doctor said I have to because I'm fat. So does anybody have any questions? Last time I finished, I was showing you a integral, and stupid me, I tried to do it on the fly without having prepped, and that's 90% of the problem. You'll see all the errors in my YouTube videos are all me flying off the cuff and trying to do a quick calculation that I hadn't prepared for. That was the case here, but I was integrating the Maxwell-Boltzmann distribution times V, so that you could find the average velocity and see that it's quite different from the root mean square velocity, which is what we determined when we were doing that ideal gas calculation. And I thought I'd give you today a little hint on how that's supposed to be done. So I'm going to start off with that, but then we're jumping into chapter 19. Probably I'll get through a good fraction of chapter 19 today, and then next time we'll finish off 19 and 20, because the part of 20 I'm doing is going to be very quick and slim. So then we'll go straight from there to quantum mechanics, because we don't have much time when we get back. The last day of classes is December 17th. So when we get
I just had a logistical question. So the only exam we have left is the final.
Yeah, as far as I remember, there might be. I thought I had another. Oh, I think what I do is I make up a test that's sort of the parts of quantum mechanics you need to know. And I don't know if I remember making that into a test, or if I had just made a practice test for it or what, but I might make a test out of it and then say drop your 2 lowest online tests or something. But either way, I'm trying to make sure y'all get tested on quantum mechanics, but maybe not on the final, because the final is stressful enough being comprehensive.
Question about that.
Yeah.
Is your final going to be on the 14th or the 16th? Because the syllabus says it's on the 14th.
Yeah, I try to do it on the earliest day, and then that gives me an extra day in case someone can't make it. I could even do it before, because it's actually going to be open to you, that day, the 14th. Yeah, because the 16th, 17th is a Friday. So yeah, it'll be open to you on that 14th. But if you need to take it early, I can set up a separate version of the exam for you to take it early or to take it late or something like that. But I really want everybody done by the 14th. That gives me plenty of time.
Okay, so the 14th it is then.
Yes, 14th. Anybody else have any questions? So yeah, when we come back, we'll have the 30th and the 2nd. I'm thinking the 30th of November, which is a Tuesday, we'll probably finish off 19 and do the little bit of 20 that I do. And then the 2nd of December, we'll do quantum mechanics, the early quantum mechanics chapter. And then the 6th, or excuse me, the 7th and the 9th, we'll probably finish the early quantum mechanics and then do the quantum mechanics and the quantum mechanics of the atom. So hopefully we can get in 3 chapters of quantum mechanics, but we'll see. So either way, like I said, I'll make that test available to you for quantum mechanics, whether it be a practice test that you're grading or whether it be a practice test and a regular test. I'm not really sure yet, but we'll make something out of that. Chapter 20 homework should not be due tomorrow. No, that's got to be fixed. Chapter 19 should not be due tomorrow as well, or anytime in the near future. I think I'm going to make chapter 19 be due on our Tuesday class, so it'd be the 6th. Oh, wait a second, I'll come back to that day. No, it'll be it could be the 29th, but I don't think I'm going to do that. I think I'll move the 19th to December 1st. So the chapter 19 homework, the concept should be ready I'll do the concepts by the 1st and maybe the actual problems by the 6th. Okay, I'll try to remember that, and that's what it should be, but definitely not chapter 20 yet. And the chapter 20, most of it's going to be done from your reading and doing the homework. I'm going to give you the sort of the skeleton of it. So hopefully that works out okay for you guys. Any questions on anything else? All right, so let me start off by showing you this little technique of integration by parts that you're going to do when you try to do the Maxwell-Boltzmann distribution. So I'm going to turn on my document cam. And basically, the Maxwell-Boltzmann distribution is here. The Maxwell-Boltzmann distribution, which is really neat, by the way. We have Bose-Einstein statistics, we got Fermi-Dirac statistics, and we have Maxwell-Boltzmann statistics, and all of them are different, and they all come from just sort of taking and calculating the probabilities of having, n particles in one energy level, q particles in another energy level, and then figuring out what they are. And they literally make no assumptions about individual atoms or molecules, and then lo and behold, you get this cool answer like this, which is 4 pi n, where n is the total number. M is the mass of the particles, 2 pi kt to the 3/2 power, times v squared e to the negative mv squared over 2 kt, which you can see that's just kinetic energy up that, negative 1/2 mv squared over kt. That's the Maxwell-Boltzmann distribution. And it's really, once you multiply it by dv, it's the probability of finding a velocity between v and v plus dv, right? So if you want to calculate the average velocity, v bar, that's going to be the integral of v times f of v dv over n. So if you wanted to calculate the average velocity squared, you put a v squared there. If you wanted to calculate the average velocity cubed, you put a v cubed there. So that's just a fundamental idea in probability. When you have a continuous probability distribution, you multiply the probability distribution times whatever you're wanting to average to get it. So in this case, you can see what's going to happen. It becomes 4 pi n m over 2 pi kt to the 3/2 over n. So you can see automatically the n's will cancel out, times the integral. Now there's already a v there, but I want to add another v. So that's going to be v cubed e to the negative mv squared over 2 kt dv. And you're going to integrate it from 0 to infinity. So the integration by parts is the integral of u dw equals u W minus the integral of W du. And as I told you before, the trick is trying to make the dw into something that's easy to integrate and making the u into something that you're probably just going to differentiate. So what I would recommend you do is you take this integral part, which is the integral from 0 to infinity of v cubed e to the negative mv squared over 2kt dv. What I would do is say that's the integral of v squared times negative mv over kt. But since I multiplied by negative m over kt, I got to multiply by kt, negative kt over m out in front. So notice that that cancels out with that negative kt cancels out with that negative and that kt. So we got everything like we want, and now it's e to the negative mv squared over 2kt dv. So what I want to do here is I want to make this right here, I want to make that into my dw. And then w is just the integral of dw. But you can see that might not be that easy. I got to do an integration. I mean, I got to do a substitution to make that. I'm going to make this function right here, negative mv squared. I'm going to make that like x. And then the derivative of x dx would be this part. So I'd have this part times dv makes my dx, and that part makes my e to the x, and the integral of e to the x is just e to the x. And then of course that means this part right here is going to be u, and that means du is going to be 2v dv. So that's how that's going to work. So I end up getting, I'll go ahead and keep writing in red, negative kt over m, that's out in front, times the integral of v squared times, now what I'm going to do is say let x equal negative mv squared, oops, wrote my squared too early, negative mv squared over 2kt, then dx is equal to negative mv over kt dv. Okay, so now what I have is this whole thing just becomes e to the x dx in that new variable. So now we use the integral of u dv, or dw, excuse me, I forgot I changed it, is equal to u w minus the integral of w du. So the u is just going to become the v squared, and the w is the integral of e to the x dx, which is just e to the x. That's e to the negative, excuse me, m v squared over 2kt. When you do these have to be evaluated at 0 infinity as well, minus the integral of w. Now we just found out w was in fact e to the negative m v squared over 2kt times du, which is now 2v dv. So now you see at this point, I already have the v out in front. So all I got to do is again multiply it by negative kt over m, and that'll make this be the derivative that we, or the dx that we need. So I can do another integration by substitution, and we're done. Okay, you can also see here as v approaches infinity, which is supposed to be the first case, this e to the negative v squared is going to go to 0 way faster than that v can get really large. So this first term is going to be 0, and the second term is both going to be 0. So that's an actual 0. So the ultimate answer here is just negative 2 times the integral of v e to the negative m v squared over 2kt dv. So what I have to do is, like I said, multiply by a I already got the v, so I want a negative m over kt, but I also have to multiply by a, I'll do it right here, by a negative kt over m. That and that cancels each other out, which means that's okay what we just did. But now I've got negative mv over kt, which is a differential of that. So I can say, all right, this is going to be positive 2kt over m times negative mv over kt e to the negative mv squared over 2kt dv. And I'll say let x equal negative mv squared over 2kt, then dx is going to equal to negative mv over kt, which we already have, times dv. So now I've got equals 2kt over m times the integral of x, or excuse me, the integral of e to the x dx, which is just 2kt over m times e to the x, which would be e to the negative mv squared over 2kt, evaluated from 0 to infinity. So I've now gotten all this integral. So my average has now got to be basically that times this integral. So I'm going to say v bar is equal to 4 pi m over 2 pi kt to the 3 halves. Now at this point, I had negative kt over m was here, and it looks like I just jumped straight from there and left off the negative kt over m. So I'm gonna put that negative kt over m back. So I'm gonna say times negative kt over m times 2kt over m times e to the negative mv squared over 2kt, evaluated from 0 to infinity. Keep these lines separate here. When I evaluate this at infinity, of course, that goes to 0. But when I evaluate it at 0, it goes to 1, because e to the 0 is going to be 1. So in fact, all I get is the ultimate negative sign, which I already had a negative sign here. So that's going to make that positive. So I'm now going to say 4 pi m over 2 pi kt to the 3 halves power 4 k squared t squared over m squared. Oh, actually, no, it's only one of those had a 2 in it, so it should be 2k squared t squared. I've just multiplied those two, and remember the negative canceled out with the negative that came from this, and that should be it. Now we can start doing some cancellations. I'm going to get 4 pi. This would be m to the 3 halves minus 2, because that's an m down there. This would be 2 pi, which I'll leave right there. I'm leaving the 4 pi out in front as well. That's to the 3 halves. So I'll just leave that. Well, actually, I'll just do like this. I'll say 3 halves. And then I have a kt to the 3 halves And since it's on the bottom, up here is on the top, so that's going to be -2 as well. And then I'm also going to have a, if I pull it inside the, well, I'm not going to pull it inside the 3 halves. I have that. So I'll just do that. So now I can start computing this junk. I'm going to say this is 2 squared pi over 2 to the 3 halves pi to the 3 halves, so I can make sense of those two. M to the 3 halves minus 2, that's M to the 3 halves minus 4 halves. So that's M to the -1/2. So the M would be in the bottom and have a 1/2 there. KT to the 3 halves minus 2, that's going to be KT to the -3 halves. That means the KT is going to be up on top and it's going to be to the 1/2 power as well. And then I've got that other 2 that's just up there. So that's going to be a ×2 up here. So I can now say 2 times 2, that'd be 2 cubed. So I'm going to say 2 to the 3 power minus 3 halves. I'm going to say pi to the 1 minus 3 halves. And that takes care of all that junk and that junk. And this over here becomes the square root of KT over M, which is good because that's part of what we expect the answer to be. 3 halves would be the same thing as 6 halves, or 3 would be the same thing as 6 halves. So 6 halves minus 3 halves is just 3 halves. So I'd say 2 to the 6 halves minus 3 halves is 3 halves. And pi to the 2 halves minus 3 halves would be pi to the -1/2. So what you can see is this 2 is going to become 2 cubed inside the square root. So I get 8 KT over pi M square root. That should be what the actual average velocity is. And that turns out to be exactly the right answer. So that's how that's done. That technique of integration is something we should all know. Just to be able to function in the rest of your classes, you need to know the integration by parts. The integral of u, I usually say the integral of u dv equals uv minus integral of v du, but I had a v in there, so I just changed it to w. But it's basically the product rule for derivatives integrated. So that's another way of easily remembering it. But that does ultimately give us the right value for the V bar. Any questions on that? Today is the 11/23/21, and this is PHY 242 D01B. So I've got that written up there, so it'll be easy to find next time. And that brings us on to chapter 19. So chapter 19 is basically the first law of thermodynamics. So we want to talk about that a little bit. It's called heat in the first law of thermodynamics. So let me discuss with you what that means. So first off, we're going to introduce the idea of heat. Heat used to be in the 1700s through 1800s. They thought of it as a fluid that flowed from one place to another. Oh, I just noticed the chat. Hold on, let me. Chapter 18. I would say chapter 18 concept questions would, yeah, actually, I'd say all of chapter 18 is reasonable to be done by tomorrow. I tell you what, this interferes with your Thanksgiving holiday, but I will push the 18th back to actually I'll push it back to Sunday, even though you're a Tuesday and Thursday class. I'll push it back to Sunday night. So you can, if anybody doesn't have it at chapter 18 done, then I'll push it back there. Okay. All right, so back on task, heat and thermodynamics. So they originally thought heat was like a fluid flowing from one object to another, and they call it the caloric, and that's where we get the unit of heat called the calorie. And then they had an entirely different thing that they thought as mechanical energy, which they measured in joules. And that was mostly developed by James Prescott Joule, who was in fact a brewer. Specifically, he brewed beer in London area. Actually, I don't think it was London. I want to say he was Scottish or Welsh or Irish or something. I don't know. But anyways, it might have been in London, but I don't want to insult, the other parts of Great Britain by saying he was in London when he was somewhere else. So I'll just leave it at that and say he was somewhere in Great Britain. All right. But he made a beer called Jowls, in fact, Joules. And I think you can still buy Jowls over in Great Britain, but that's kind of neat that he had that. But he also did a lot of contract work on trying to figure out how to get cannons to dissipate heat pretty well, so people could still use cannons after they fire it once. As you can imagine, you fire a cannon a couple times, it gets pretty freaking hot, and it's kind of hard for people to touch it. So he was working on that kind of stuff too. But what he did was he went ahead and did a little experiment and discovered that, in fact, heat that we know of as caloric or calories is actually equivalent to mechanical energy, which we know of as something we measure in joules. And the experiment he did is basically and it's really, really hard to detect. So he was pretty phenomenal as an experimenter to pull this off. But basically he made like a little propeller that ran into a container of water. And the little propeller had like a spool on it, and you'd wrap string, if you will, or rope around this shaft of the propeller, and the propeller of course would be held nice and vertically. And then he took that wrapped rope or string or whatever, ran it over a pulley and hung a weight from it, and he would let the weight fall down a height h, so that the mechanical energy that was put into the system was m times g times h, which we know in joules. And then he would actually measure how the temperature of the water changed. And lo and behold, the water changed ever so slightly, but did change and went up. And he set that equal to the equation that we know of as the heat required to raise the water of temperature, or the temperature of water, the water of temperature, of course. Yeah, the temperature of water. So that was Q equals MC delta T. And lo and behold, what he found was an equivalence of heat and mechanical energy. So today, that's so far in the past for us, we just treat this as a conversion between calories and joules. But in fact, it's so much bigger than that. It's a whole different paradigm. It's an idea that heat and mechanical energy are the same thing. And that's what we're starting to study. So that equivalent that he found was 1 calorie equals 4.186 joules. Dang it. Okay, so let me turn on my document cam so I can start writing some stuff. Okay, so what he found was that 1 calorie is equal to 4.186 joules, or you could also say it this way, 1 kcal, which I'm going to write a couple different ways here. 1 kcal, crap. Terminix is here. Shit. Oh, sorry about that, folks. Terminix is here. I'm going to have to stop in a second. My dog's going to go crazy. 1 calorie is equal to, that's the calorie that we eat. Notice the capital. That's equal to 4.186 kilojoules. Okay, so let's pause for 5 minutes. I'm going to take a break for 5 minutes. I'm sorry about that, folks. I'll be right back. Okay, sorry everyone. I thought I asked them to come in the afternoon, but they didn't explicitly say they could do that. So since this is being recorded, it's not a big deal if y'all stepped off for the whole 5 minutes. You're going to be able to catch up anyways. But what I was saying was what Jewel found was that the calorie, a unit of heat, was equivalent to a certain amount of mechanical energy. And this was what we now treat as the conversion factor. But in reality, it was a big paradigm shift that it says heat and mechanical energy are equivalent. So you can say, well, let's say a bullet has a certain amount of kinetic energy, and then it embeds itself into a tree. Where did all that energy go? Well, it went into deforming the bullet, and it went into deforming the parts of the tree. And then in addition to that, it went into heating up the tree. So that's a whole new way of thinking about things. But doing that, if you used a very specific type of material, you could actually do all that and determine how fast the bullet was going initially. So that's sort of a big deal. Anybody have any questions about that part? All right, and you can see the little drawing of his experiment in your book, where basically he actually had like 3 paddles they drew in this drawing for propellers. But basically any kind of propeller system would work, but you got to be very, very careful. You got to make sure, because this is such a small amount of energy going into the water, you got to make sure that that water container isn't getting heated up from something else. So you have to have a really good like thermos type container, maybe a double walled container or something like that, so none of the heat can come from the outside air. Or you'd have to make sure the water and the air in the room are all the same temperature initially, so that heat can't flow from that. So it's not an easy experiment to do, but at the end of the day it was done. Now the other thing that we need to understand about thermodynamics is there turns out to be this quantity called internal energy. So any substance and any object, in fact, has a total amount of internal energy. And really what we normally count it as is the sum of all the different types of kinetic energy that the individual molecules have within it. So the individual molecules or atoms that make it up, they're all moving, and they all have, for instance, a 1/2 mvx squared plus a 1/2 mvy squared plus a 1/2 mvz squared. That's the 3 components of kinetic energy translational. But if it's actually a body molecule that actually has sort of shape and structure, then it can actually rotate about one axis. It can rotate about another axis. All those are different things as well. Then it can have vibratory motion as well. So the individual, like if it's a dumbbell, the individual atoms can do this. That's another type of energy as well. And the internal energy is basically an accounting of that energy. So for instance, we can say internal energy is equal to, if we consider, and notice your book's using E equals I internal. I'm gonna turn on my document here. Document came here. Your book's using E internal instead of U. A lot of books use U for the internal energy, but that gets us confused with potential energy. So I don't want to necessarily do that. So that's why we're using E internal. And if the particular object that we're dealing with has N atoms or N molecules, we expect that internal energy to be equal to 1/2 mv bar squared. And you guys recall that. Cosmo? Sorry, is that dog as loud to y'all as it is to me? Are y'all unable to hear me? Are y'all unable to hear me when I'm talking, even when that dog's barking?
Yeah, we hear you.
Okay.
Yeah, we hear you. We hear the dog too, but we hear you as well.
Okay, I apologize for that. I closed the door and hopefully he stop barking, but he's not a smart dog. All right, so this is the kinetic energy, and we learned last time, or we derived last time, that the average kinetic energy, which is 1/2 m v bar squared, remember that's the root mean square velocity, was equal to 3/2 kT. So from that we can say E internal is going to be equal to 3/2 m kT. So that's the internal energy, more or less, of an ideal gas. But we also learned that N is really little n over Avogadro's number. So you can actually express it in terms of R as well and say it's E internal is equal to 3 halves nRT. All right, so that's the E internal. And that's a new expression for us to use. And that also gives you some understanding of internal energy. Let me take him for a second. I'm going to put him with his grandmother. He's getting way too loud. I'll be right back. I can't do this. No. I am sorry again about that, folks. Luckily, my wife's mother is currently living with us, so she can help me out on that. So what we were talking about here is this is the internal energy, more or less of an ideal gas, but it turns out to be pretty accurate in terms of experimental evidence. So it's only when you get near those cold temperatures or those low pressures where the atoms and molecules get close enough together that their attractive forces muck things up a bit, and then it is different from there, from that. But other than that, it actually holds up pretty well. And in fact, you can then go on and use this to explain, for instance, when you add heat to a system, what actually happens to it. So if I add heat, for instance, to a chunk of metal, the internal energy is definitely going to go up because you see the internal energy is directly related to the temperature, right? But by looking at this, you can see, oh, this is suggesting that at least 3 parts of it are going to kinetic energy in the X direction, kinetic energy in the Y direction, and kinetic energy in the Z direction. And in fact, there's other ones that aren't related to temperature that allow it to go other places. So in fact, when you look at a water molecule, which you can sort of picture a water molecule like this. So there's the oxygen, and there's the hydrogen, and there's the hydrogen like that. You can see that in fact, when you add heat to it, it's going to increase the internal energy based on, 3 parts of the energy, 3 equal parts of the energy going into 1/2 mv(x squared, 1/2 mv(y squared, 1/2 mv(z squared). But in addition to that, there's a chance that this is going to wobble in and out, and that doesn't account for internal energy. This is going to wobble in and out. That doesn't account for internal energy. This is going to rotate about this axis. That isn't accounted for by internal energy. That could rotate about that axis. That's not accounted for by that internal energy. And in fact, oh, he's spraying stuff, gotcha. And in fact, you could also oscillate this molecule, say about this axis, or I say oscillate, you could rotate this molecule about that axis. But all those different degrees of freedom, all those different ways that the water molecule can move are other candidates for where the energy is going. So if you think about water being an insulator, maybe we come up with, say, 9 different ways that energy can be taken in, 3 of which are the translational kinetic energy that I talked about, sort of the center of mass of this going to the right, going in the Y direction, or going in the Z direction. But the rest of them, which are equally probable, all go into something else, not heating it up, in other words. So that's why the specific heat of water is so high. And what is specific heat? Well, specific heat is the heat required to raise 1 gram of water. Now I'm going to try to say this as precisely as possible. It's basically the heat required to raise 1 gram of water at 20 degrees Celsius to 21 degrees Celsius or something like that. I think it used to be 14.5 to 15.5 or something like that. But I'm going to say 1 gram of water from 20 degrees Celsius to 21 degrees Celsius. And I'm just say roughly, because I'm not going to go look up the historical record and see exactly what it is, but it's for a very specific temperature range. And if you're close to that, it's always going to be that same amount. And in fact, the specific heat of water is indicated by the lowercase c, and it's lowercase because it's per gram. If you just had without the per gram in there, it'd be a capital C, but the specific heat of H2O is 1 calorie per gram per Celsius degree. And that's what the idea of the calorie came from, is it specifically, we said it's going to be exactly 1. Well, it turns out it's exactly 1 only in this range, but it's, you know, probably 1.000, maybe all the way up to 30 degrees Celsius and all the way down to maybe 10 degrees Celsius. But if you really wanted, you know, very precise data, maybe you have to look up exactly what it is in each of those ranges. But that's the specific heat. And you think, well, that's not very impressive. But then you look at the specific heat of aluminum. So C aluminum, and that's 0.22. Or if you look up copper, that's really bad. That's 0.093. So you can see, oh, wow. Again, these are both in calories per gram Celsius degree, calories per gram Celsius degree. But you see clearly that 1 is really large compared to these things. So this is 93 tenths, hundredths, thousandths, 93 thousandths, whereas that's a whole 1. So water is a really great insulator. And the reason it's such a good insulator and not that good of a conductor is because it's got all these different modes of energy for the energy to go into that aren't related to temperature. So, and the equipartition theorem, remember we talked about that before, equipartition theorem basically says, hey, that when you have, you know, like 10 to the 25th molecules or atoms, that's such a huge ensemble that's really what statistics is meant for. And the probability of more energy going to the kinetic energy in the X direction than goes in the kinetic energy in the Y direction is essentially 0. And the probability of the kinetic energy in the X direction going in the X direction is different from the kinetic energy due to this rotation. That's essentially 0 as well. So what that forces is that each of these various modes of energy, all the things that are, you know, some quantity squared. So like 1/2 k x squared, 1/2 I omega squared, 1/2 m v squared. Notice they're all something squareds. So there's 3 dimensions of this, there's 3 dimensions of that, there's 3 dimensions of that. You see, you get around 9 of them suckers, and there can even be more depending on how your molecules is constructed. But because of all that, every one of them is going to get an equal amount of energy, and only 3 of those are going to result in an increase in temperature. So yeah, the specific heat of water is really high because it can do so many things with the heat coming in. Does that make sense? All right, so you might wonder, for instance, here's an example. What is the final temperature of a cup of coffee. And notice I said cup, that's an actual official measure, even though it seems to have written cop. A cup of coffee at 90.0 degrees Celsius after a tablespoon of 0 degrees water is added. So one of the fundamental rules that we use, I call it fundamental, just sort of being funny there. One of the rules we use is whenever you're dealing with any kind of drinks, they're essentially water. And you'll see that there are actually trace amounts of other things. So it's fairly accurate to call it water. You might want to, mix in maybe 1% of sugar or something like that, but you can just treat everything as if it's water. So a cup of water is supposed to be, I remember a pint is 500 milliliters, so a cup should be 250 milliliters. So 1 cup equals 250 milliliters. And I'm going to assume that's right. If y'all want to Google that and confirm or deny it, that's fine too. But I'm going to go with that. Actually, do tell me, in fact, if someone can Google it quickly, but I'm thinking that's what it is. And a tablespoon is actually supposed to be, I want to say 45 milliliters. If someone could look up that would be awesome. 1 tablespoon. I think a teaspoon I want to say was 15 milliliters. And then a tablespoon is 45 milliliters. So I'll put little question marks over top of that. Okay. The reason why is because I know what the density of water is. I'm going to Google it real quick because, why not? Unless someone's already done it for me. Anybody figure that out for me yet? Crap, babies. All right. 1 tablespoon. I was wrong. It was the tablespoon was the 15 milliliters. So tablespoon's 15 milliliters. And let's say cup to milliliters. The Google machine is awesome.
Yeah. I got 237 for the cups to milliliters.
Okay, cool. Yep, that's what I just found as well. So 237. I think they use 500 milliliters specifically because that's half a liter, and that's using the British system, or actually the SI system. So that's probably why Aquafina bottles are now 500 mil or 250 to 500 milliliters, stuff like that. So not to be confused with the Aquafina, who's a person. All right, so we've got these values. Now the reason I say that is I happen to know that the density of water, rho H2O, is equal to a bunch of different things, but it's 1 gram per cubic centimeter, which everybody should know. It's also 1,000 kilograms per cubic meter. So it's literally a ton of water. Okay. But it also happens to be 1 kilogram per liter. Or it also happens to be 1 gram per milliliter. So that's the one we're going to use because we want to know what the mass is. So what I know is that Q is equal to MC delta T. What that means is the heat required to change a mass M, a temperature change of delta T, is equal to M times C times delta T, where C is the specific heat of the substance. So in this case, I'm going to say that one side is losing heat, so Q lost is going to be equal to Q gained. Now, I'm assuming, of course, that all of the heat lost by the coffee is gone into being absorbed by the water that was really cold. Now, in reality, to do that, you'd put it like in something called a calorimeter and all that good stuff, but it's going to happen pretty quickly. So I don't think we're too far off. So what I'm going to say is the mass of the water that I put in, that's going to be, of course, since 1 gram is equal to 1 milliliter, I have 200, excuse me, I have 15 milliliters of water. Milliliters times 1 gram per milliliter times 1.00 calories per gram Celsius degree. And its temperature is going to change to, and what I do here is notice what I set equal the loss and the gains, everything should have a positive value. So even though the formula is delta T and delta T means final minus initial, when I do it this way, instead of the sum of the heats equals 0, which I prefer, by the way, this way, not the sum of the heats. When I do it this way, I got to make sure the delta T is a positive. So I know that the ice is going to warm up, or excuse me, the water that's at 0 degrees Celsius and almost ice is going to warm up. So the final temperature will be the larger one. So I'll put T final minus 0.00 degrees Celsius. And that's got to be equal to 237 milliliters times 1 gram per milliliter times 1.00 calories per gram Celsius degree. And this one's going to get colder, so I'm going to say 90.0 degrees Celsius minus T final. I can set those two equal, and I think you can see what's going to happen is these two C's are going to cancel out, and I basically just get 15 TF is equal to 237 times 90.0 minus 237 TF. I pull the TFs over here, I'm going to get 247, 252. So 252 TF is equal to, now I'm going to take my 237 times 90. And that's going to be 21,330. Of course, that's only 3 sig figs, so really it should be these last two are there. I'm ignoring the units because I knew the units worked out initially. So really the T final is going to be 21,330 over 252. And that makes sure adding 237 and 15 gives me 252. It did. Okay, so I'm going to say 21,330 divided by 252 is equal to 84.64 degrees Celsius. So you only decrease the temperature by about 5 degrees. But that's because the specific heat of water is so high. So not only is it good that you used water to cool it down, that's good because water would have the best ability to bring it down compared to many things. And in fact, the only things, actually, I don't think your book gives a single thing in their specific heat table that has a specific heat higher than water. Nope, not a single thing. But there are things, of course, we've made, for instance, anybody think of a liquid that might have a better specific heat than water? Something you might use in your motor car?
Or oil, gas.
Gasoline?
Yeah, all of those I suspect, but definitely the fluid that you put in your radiator fluid, which I think is ethylene glycol and some other stuff like that. So those things you suspect, yeah, antifreeze, yeah. So those things probably had a larger specific heat, but your book didn't list those. And evidently they're sad because they taste sweet and dogs drink them and die. So don't spill your antifreeze and coolant and all that good stuff. So yeah, coolants, and I suspect oil, I haven't looked it up, but I suspect oil would too. And they definitely have to have a higher boiling point, or else we got real problems, right? If you get a gas boiled and turned into a boiling gas in a closed container that's supposed to be cooling down your engine, that's not going to work very well at all. So anyways, that's one of the types of problems you can solve. And this is called calorimetry, when you're actually trying to account for all the heat losses and gains. The normal way they do calorimetry, or the normal way most books introduce calorimetry, I don't care that much for, but it's delta Q is equal to 0. That's the way they normally do it. So what you'd say is Q1 plus Q2 plus Q3 plus ... all sum up to equal 0. And when you're using formulas like this, the MC delta T, that's easy peasy. This all works great, right? Because you just do final minus initial, and it'll automatically tell you whether it's losing heat or gaining heat. So all these positive and negative signs work out perfectly. The problem is there's another scenario that comes off, and it's called latent heat. So latent heat is basically some additional amount of heat that must be added to make something change state. Okay, so for instance, if you bring water into the picture and you take, for instance, let's say heat added, and this will be temperature. Okay, what you'll see is water basically does this sort of deal. So this is liquid water first that I'm going to start with. You go up, 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 and then you reach a critical temperature, 100 degrees Celsius. Okay, at that point, the temperature stays exactly the same until a latent heat is added. In other words, you've got to do the MC delta T. That's that linear response right there. You got to do the MC delta T to get it from 0 degrees Celsius to 100 degrees Celsius. But then while it's boiling, every bit of water stays at exactly 100 degrees Celsius. That's why we cook with boiling water, because we know, hey, if I boil something in water, I know that water is maintaining a fixed temperature of 100 degrees Celsius or 212 degrees Fahrenheit. So if I leave the mass of what we're cooking in there long enough, eventually the entire thing will reach that temperature, and that temperature is high enough to, you know, kill botulinum and all sorts of other bugs and stuff that could be in pork or something like that. And now it's the worst way to cook because it almost always sucks all the flavor out of it, but still it does work for things that you don't care that much about, just need to get them to a safe temperature. And then once that latent heat occurs, now it's actually steam, and what you see is the thing goes linear again. Okay, now it also does the same thing right here at 0 degrees Celsius. It would be level, and then it would be liquid temperature and have another a different slope over here, because it turns out the specific heat of ice is different than the specific heat of water, which is different than the specific heat of water vapor. As you can see in that table, water has a specific heat as a liquid at 15 degrees Celsius of about 1. Steam has a specific heat of about 0.48 at 110 degrees Celsius, and ice has a specific heat of only 0.5. So it's still pretty high compared to metals and stuff, but it's nowhere near as high as the liquid. So when you start to do this and you're changing states, it becomes a little more confusing for you to decide which way is negative and which way is positive. So what I always use is Q lost is equal to Q gained. So I can almost always just think and say, okay, well, it takes more energy put into the system to take it from a liquid state to a solid. I mean, take it from a liquid state to a gaseous state. So I know if something's going to change from liquid to a gas, that thing's gaining heat. So I put it on this side. But it's a little more confusing when you start to think about whether that's a positive Q or a negative Q. So that's why I've found that my students do better with this than they do with the summation of the Qs. You can use anything you want, but the latent heat comes in a lot of different forms. As you can imagine, the latent heat, for instance, could be the heat of fusion. And of course, I think you can see the heat of fusion is going from basically a solid to a liquid. So, or actually, I should say it the other way, going from a liquid to a solid. Okay, there's a heat of fusion, there's a heat of vaporization. and that would be going from a liquid to a gas. But there's also a heat of sublimation. Anybody know what that means?
Straight from solid to gas.
Exactly. Anybody know of a substance that does that?
Ice.
Yeah, the dry ice does. Exactly. The one you use.
Regular ice does it as well in vacuum.
Oh yeah, yeah. Real ice does it definitely if the pressure's low enough. In fact, yeah, if you took a pot of water and stuck it on the surface of Mars, it would actually immediately boil away, even though the temperature is way lower than 100 degrees Celsius. So yeah, you're absolutely right. It does sublimate in under the right conditions. But CO2 is the one
You can
that
even does it
happens-
on Everest occasionally. If the pressure differential gets low enough, it starts
really?
sublimating.
I didn't know Everest got low enough pressure, but that's cool. Yeah. And that is what they use. They use either that or the boiling point. So for instance, when they were trying to look for the source of the Nile, they would follow the Nile River of all its little tributaries and keep going. And once they get to somewhere they felt like was pretty high, they would boil water and see what temperature it boiled at. And of course, the higher you go, the lower the temperature it boils at because the pressure is lower and lower. And then once you find the highest spot, then that'll have the lowest boiling point, and therefore you'd say, okay, well, this is the source of the Nile because all water has to flow downhill. But yeah, that's exactly right. Cool. I didn't realize we got low enough, but that makes perfect sense. I read Into Thin Air, and I know the atmospheric pressure at the height of Mount Everest is basically not enough to support life. If you went up, if someone just dropped you off there by transport or helicopter or something, and helicopters can't even always fly there. But if they just dropped you off on the top, you'd probably die within a few hours because you couldn't get enough oxygen. So yeah, that's cool. All right, so that's another idea that has to go on. So one of the problems I like to work is how much ice does it take to take a gallon or 5 gallons or 10 gallons of 100 degrees Celsius tea and make it iced tea, meaning tea whose entirety is liquid at 0 degrees Celsius, but not quite frozen. So that's a neat problem you can actually solve. I don't have time to do it right now. That's probably one of the things I'll save for next time. But that gets through the major concepts of what this chapter is about. Now, the first law of thermodynamics is the next major concept, and I need to discuss that as well. And we'll do more of the problems in our next meeting, as I mentioned before. I don't remember what I said in the last paper. Oh, well, there it is. Okay, so the first law of thermodynamics, and it's going to be different, for instance, in your chemistry class than it is in your physics class. The first law of thermodynamics. Now, what it normally says is basically, I'd like to use differentials, but I need to explain something about that. So I'm going to use a delta for right now. So the change in internal energy is equal to the heat added. Notice that wording, heat added minus the work done by the substance. The reason why I take the time to write that and explain to you to listen to that is because when you do it in chemistry, they'll say Q plus W. In that case, they're using the work done on the system instead of by the system. So that's why you'll see in chemistry, they do internal energy is equal to Q plus W. And in physics, we do internal energy is equal to Q minus W. Okay. And what this is really is just conservation of energy. Okay. And it tells you, you know, what can happen. Well, it turns out if you add heat to a system, that can either cause the system to do some work to take some of that heat away. So for instance, you could heat up a piston of gas that piston is going to have all those gas molecules raise their temperature so that their average kinetic energy is higher. That's going to push the piston head up, 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 up. That's doing work on the system. And if you did it such that the temperature didn't change, because we know for an ideal gas, temperature is the only thing that internal energy depends on, then all of the heat added must go to work done. Well, that turns out to be a violation of the second law of thermodynamics, but that's neither here nor there. But you can see that that equation seems to allow that, right? You can also have work done on the system as opposed to by the system, and that becomes what we call a negative amount of work. And since this is the negative of a negative, that becomes positive. So if you actually take a piston of gas and you call that the gas in there the system, if you actually compress that gas, you're doing work on the gas. And if you do it in such a way that no heat's added, then all that work will go into increasing the temperature of the material. Now, if you don't do those two extreme things, you just add heat and spontaneously the piston full of gas expands a little bit, but it also goes up in temperature. Well, the temperature change will occur here, and the work dissipated will go in this slot, and the Q is here, such that the change in internal energy is equal to the heat added minus the work done. That is minus the work done by the system. That is the first law of thermodynamics. Now, your book takes the time to write it this way, and right here, everything's golden. However, what I do at this point is not what your book does, but your book does give a comment on the on a little footnote at the bottom. I write d bar Q minus d bar W. And the reason why is these are not exact differentials. If you've had differential equations, you've heard that expression before, but you didn't probably right then you didn't think of it as being related to this at all, but in fact it is. What this means is there's not a Q as a function of PV and T that exists so that you could say integrate it from point A to point B and it's going to be independent of path. Same thing with the W. There's not a W as a function of PV and T that you can integrate from A to B and the amount of work done would be independent of path. Or if you went in a closed loop, it wouldn't be necessarily zero. These are not exact differentials, and it does mean the same thing as the exact differentials that we have in exact differential equations. And when I say exact differential equations, they'll say something like 3x squared dy plus 7x y dx equals 0. That's an equation that might be considered an exact differential equation, but what you got to do is take the derivative of this with respect to x and see if it equals the derivative of this with respect to y. If they are, then they're exact differential. If they're not, then they're not. Okay, but you can see now, oh, that's why they had that stupid form with a little dx or dy in it instead of having a dx and a dy in it. So this is actually the more accurate way to write it in terms of a differential. You should write or just know that you're not going to find Q as a function of PV and T. This way is always right. No Q of PV T exists, and no W of PV T exists. So these things where that exists are called state functions, equations of state. They are functions f of P, V, and T that only depend on the pressure, volume, and temperature. Example is internal energy. Another example is entropy. The ideal gas law is an equation of state. So you could say this whole thing's an equation of state, and then you could say, you might want to call it something like PV minus nRT is equal to F of PVT, but it actually equals 0. That's how you can state it as an equation of state. You see, oh, that's a function of PV and T. It just happens to always be equal to 0. So that's what equations of state are. And when you have an equation of state, you can automatically write a D of that equation of state. If you don't have one, then you have to write it like a D bar. Okay. So that is what the first law of thermodynamics is. And that tells you, in fact, how you can solve problems with it. The big thing to remember, like I said, is that this minus is because it's work done by the substance or by the system. So make sure you keep that in mind, because you're now in a good spot where you can basically answer all the conceptual problems. Okay. You can now figure out things like the first law of thermodynamics used for calculating work. If the process is isothermal, that means the temperature isn't going to change. That means this has to be a constant, because we already found that E is equal to 3/2 nRT. So isothermal, that's one word we'll use. And since delta E is equal to 3/2 nR delta T, delta E internal equals 0. So that's a big thing that you need to know. Isothermal processes mean the change in internal energy is going to be 0. There's other processes. There's an adiabatic process. That implies no heat added or lost. Which means D bar Q, which equals Q, is equal to 0. So in that case, you just get internal energy is negative of the work done. There's an isobaric process. Which is also called isovolumetric. Actually, it's not equivalent. Isobaric is supposed to be constant pressure, as you can see by bar being in the word. So this is constant pressure. And the other one means constant volume. The reason why we say that, or we group them together, is if you make a P versus V graph for isobaric, then it looks like that. So this is isobaric. And if you make a P versus V graph for this one, that's isovolumetric. I misread it for a second. That's why I put them together like a slash, like they were equal. There's something called isochoric, and that's kind of an ancient phrase that's used. But isochoric, if I remember correctly, was the same thing as isovolumetric. It's just a weird word that we don't use anymore. The reason why these matter is if you try to take work as the integral of P dV, then in the isobaric case, you just get pressure times the change in volume. But if you take the isovolumetric case, then the work is equal to 0. Because remember, our typical example of work being done by the system is the gas expanding and lifting the piston head. So if the gas can't expand, that delta V is going to be 0, and isovolumetric gives you a 0 work. So these are some of the changes that can happen. You can also say in general, now this is separate from these different situations, work is equal to the integral of PdV is nice because you can take the ideal gas law, which says that PV is equal to nRT. And with that, you can change this P to nRT over V, integral of nRT over V dV, as long as the temperature and the number of moles doesn't change. And this just becomes N times R times T times the natural log of V final over V initial. So this is for a constant. Temperature, which we call isothermal. And it's an isolated gas, meaning N equals a constant. So that's sort of the big terms that we're supposed to do. And actually now our class time is up. So I'm going to go ahead and let you guys go. You can look at all this up through, we've basically gone through page 409, excuse me, 509. Basically, we're up to 19.8. So we've done 19 -1 to 19-7. So next time we'll do a bunch of examples and we'll do 19.8 and beyond and all that stuff. No problem, Vanessa. I think you might have already left, but you guys are free to go anyways, and have a happy Thanksgiving. I will check on those homework dates and set them as I said. I'll make sure 18, I'm going to push all the 18 dates back to Sunday, and I'll make sure 20 is not up yet.
Thank you.
No problem. Y'all have a good one, everybody.
You as
No class Wednesday, don't forget, for those of you who have a Wednesday class. Kendrick, do you have a question? All right, well, I'm killing it. Have a good day, everybody.